Hello. Get my slides open. So I don't know if all of you were here last course, but I guess just a quick thing of how this works if you weren't here last week. So I record these. It's already started recording now. And I'm going to post a YouTube link. I'll send it to everyone either today or tomorrow. So that way, that's why I think some people who want to watch it, they do it at a different time, or they're just, because I try to be as accommodating as possible, because I totally get that like this is kind of a weird time for everyone, but I still appreciate you guys for being here. So but yeah, just so you know too, like for anyone, any of you guys here, if you ever can't make it, don't feel bad. So I guess for today, I was going to talk a little bit about the week 2 stuff. That's typically what I do. So every Thursday, I'll talk about that week's material. I do that. I have a class on Thursday because I think it's good to kind of do it at the end of the week, because that way everyone can get, like, if they want to at least get a quiz attempt in, and then go from there. So I guess I'll start first. Does anyone have any questions at all? And then if there's no questions, I'll just probably go into week 2 stuff. It probably won't last that long. I think this week is pretty easy as compared to some of the weeks in the coming up. I think about week 6, just so everyone has a heads up on this too, week 6, your quiz is actually something that you have to write in and like send to me. So kind of keep that in the back of your mind. You might want to look at that just to get an idea. So basically it's only worth 5 points, but it asks you to draw like on a piece of paper and then send me a picture of it of like different circuits. So you can use, like, if you want to use PowerPoint or like Microsoft Paint, or you can do it by hand too, but just a heads up that like that's coming. So but other than that, hopefully this course isn't going too bad for you yet. But yeah, so let me pull up these slides, and like I said, I'll talk through kind of the week 2 stuff. If you have questions at any point, stop me. If you have I'll save some time at the end too if you have any questions about Amatrol or anything like that. So whatever I can do to help make this course easier is my goal for you all. I'm going to share my screen in a minute. Once I find what I need. Okay, perfect. So, share my screen. Perfect. So you should see my screen now. I'm actually going to move it over here and we'll make it big too. So can you guys all see my PowerPoint right now? Is that what's playing?
It looks like a background.
Oh, it's a background.
Yep.
Oh, and me. Shoot. Are we back in the PowerPoint now?
There it is.
Thanks. Okay. And present. Okay. So the main thing for this week, it's really, really simple, I think, for about half of it. And then when we get into the power stuff, it kind of gets hard. So that's where I'll put a lot of the focus in. So the first little bit is we kind of dive into a little bit more on series and parallel. So I think I spelled parallel wrong in that. I think it's P-A-R-A. Yeah, it is. So this definitely comes into play in the later weeks. In particular, when we talk about parallel circuits, there's a lot more math involved. And that's, I think, to come in the next week. So just make sure you understand this week, because next week is going to add another layer, I guess, to this. So, and this is exactly what I'm talking about for next week. So basically, when doing series and parallel, we know the main difference is that series have one single pathway and parallel have a multiple path. I don't think I talked about this last week, but it sometimes confuses people because there's alternating currents and direct currents. This is a totally different situation when you're talking about series and parallel. Alternating and direct just means that the flow of your electrons might go, different which ways. When talking about series and parallel, we're talking about like the actual pathway. So for example, in this picture, I think is a great depiction of that. So in a parallel, you might have like kind of where this, can you see my mouse where I'm like circling right now?
Yeah, you can see it.
Okay, perfect. So kind of like right here where this is called, I think it's called a node or a junction sometimes. Basically when the electrons, they're starting, let's say wherever they're coming from here. And then when they get to this node, the electrons basically have a choice. Some of them might go straight here and some of them might go this way, because basically with parallel, there's multiple pathways. So that's what it's describing. Whereas series is just, the electrons don't have a choice. They're going to go in this straight square the whole time, whereas on parallel, they don't have to. So I guess that's the main point. So if you kind of understand that, I think the visual is the best way to understand it. So series have a single path, parallel have multiple pathways. And this is just showing, like one line in the middle, but in some parallel circuits, they might be a lot more advanced than that, where you're going to have multiple different routes they can go. So the other thing about this picture that's important to note is you see those R1s, R2s, R3s. What those are referring to is your resistance. So we talked about resistance a lot last week, and how resistance, current, and voltage are your main ideas of Ohm's law, your main ideas of this course, really. But resistance, you can have your total resistance, which is kind of what we were talking about last week. So we talked about like calculating your current when you were given your resistance and your voltage, or calculating your voltage when you're given your resistance or current, you could, whatever one you wanted to solve. But what I didn't mention, and this is where this week takes another layer, is we were talking about total resistance. So in every circuit, they have a total resistance, which is, for a series circuit, the sum of all the resistors. And that's exactly what this is showing right here, where it says equivalent resistance. Equivalent resistance is the same thing as total resistance. So total resistance is just basically whatever ohm you have, remember, because resistance is measured in ohms. So it's the total amount of ohms per that whole entire circuit. And sometimes, like for how resistors work, is we have, sometimes you put resistors in your circuit for, safety purposes, or, to make sure you're not overpowering that circuit with electricity, or, whatever the reason is, but you might have different amounts of resistors, and that's what this picture is showing. So in the series circuit here, they have just 2 resistors. In this parallel picture, they have 3. So you might have 5, 6, 7 resistors in your circuit. And series and parallel both have, various different amounts of resistors. It just depends on the problem you're given. So in like real world applications, I'm sure there's a lot, like once you start doing, real world stuff, like obviously I'm sure there's like numbers, like for like what logistically you see a lot, but like just for like matters of this class, like you might have an abnormal number of resistors, just so you understand the concept. So basically the main idea is here again. So in order to calculate that total resistance, you just sum up whatever the values are for all of your resistors together. Next week, we'll talk a little bit about this. So how to calculate total resistance or equivalent resistance for parallel circuit. But this week, we're just focusing on series. So that's a little overview of what we're doing. Here's an easy example, and this is all you have to do for this course in terms of calculating resistance. But I just like to give a spiel at the beginning here because I want you to know what's to come. So it's as simple as this. So in a series circuit with a 400 ohm resistor and a 300 ohm resistor, the total resistance or equivalent resistance is 400 plus 300. So it's just a sum. So if we look back at this picture, what this is saying to us is that we have an R1 of 400 and an R2 of 300. So let's say we're looking at something like this. R1, let's say, judging by this, was 400, and R2 was 300. All we did was this equation, R1 plus R2. So that's another thing that this equation is kind of conflicting or confusing, because you see like, well, this says we have to add R3 too, but that just really is basically what this equation is telling you, is that however many resistors you have, the sum of those is going to be the total resistance. So again, it really doesn't make a difference if you have one resistor, if you have two resistors, if you have three resistors, you do the same process all the time. It's just sum them together. But again, we're talking about series circuits here, parallels next week. So that's a lot of like the quiz questions for week 2, is just calculating your total resistance in a series circuit. And all it is adding your resistors together. So same example here. So in this situation, we have 3 resistors. So this is a perfect example of how sometimes you're going to have varying different numbers of resistors in a circuit for this course and for the applications in this course. So we have 100, a 300, and a 500 resistor. So in order to calculate the total resistance, you just add all of those together. Does this make sense to everyone? Like is that clear that we're just adding it all together?
Yeah, that's clear to me.
Okay, perfect. If you can stop me at any point. I can slow down and we'll go from there. Thank you. So, okay, so this is our next little bit here. And I'm kind of jumping all over the place, I know, but I just think I'm trying to touch on the main ideas. Like I said, stop me at any point and I can explain it further. So the other thing we talk about in this course is watt hours. And basically, there's only a couple like scenarios or quiz questions, I guess, related to this. So I wanted to touch on it, but it's really not that complicated and it's not that big of a thing. So I didn't, create a ton of slides about it. So basically what a watt hour is it's your power times time. And you know this because watt or wattage is a unit for power. Hour is a unit for time. So when you see watt hours, you automatically should know right in your head, okay, that's power times time. So for example, like we have here, let's say you had a 50 watt light bulb on for 5 hours. How many watt hours have you used? All you have to do is 50 watts times 5 hours and you get 500 watt hours. That's all it's saying there. So something that I think is that I want to touch on, because I think this is really important. So whenever you see like a term like watt hours or meters per second or whatever, like if you see any type of like, it's called a derivative unit, when you have two different things in one number, but two different like things at the end, or two different words at the end. However the words are written should show you how to do the math. So this saying watt hours right now means that I'm timesing my watts by my hours. And that's why I did 50 times 5. If it said something like calculate watts per hour, per always means divided. So you do watts divided by hour. So in this situation, I would do 50 divided by 5. 50 watts divided by 5 hours to get 10. So basically, that's the main point of this, is that you should recognize that when you see watt hours, it just means watt times hours. So whatever they give you as the watt and whatever they give you as the hours, just multiply them and that's your answer. So hopefully that makes sense. And you're only, for at least this course, you're only going to ever have to calculate watt hours. You'll never have to calculate watt per hour or anything like that. But it's just, I think, a useful thing to know, especially for further classes and for math purposes. Does this make sense to everyone? It's a pretty simple idea, but just multiplying whatever your wattage is and whatever your hours is will give you watt hours. If there's no questions, I will probably move on from here. Okay, so I gotta got my little notations. Oh no, I have my clear. Oh, I should learn that for last week. Okay, so we talked about this last week, the circle. The main idea, the reason I am showing this picture again is because now this is really what we're focusing on for this lecture. And it's the power section. So a lot of the questions in the quiz, a lot of the concepts in this week are related to calculating power or using power to find other calculations. And it can be a little bit tricky because power is when square roots become involved. So basically, these are the equations that you need to know. And that it's power, or P, equals V times I, which is just voltage times current, because remember I, they write as current, or current they write as I for some reason. The next one is power equals I squared times R. So that is I squared times R. And then the third one, power equals V, which is voltage squared over R. So definitely either remember those equations or know how to derive them, but learning how to derive them is probably way more complicated. But so I would either write these down or use this if you understand all this. Basically, it's just saying whatever one's in the middle here, this equals this equals this equals this, R equals this equals this equals this. So this shows you all the equations, which is why I gave you the circles.
But why do you use them?
I'm sorry, I think you broke out at the end. Can you repeat that? Michelle, did you have a question, or I want to make sure I answer it if you did?
I was just sorry, I didn't realize my microphone was on.
Oh, okay. Do you want me to explain it more? Is there something that's confusing? I want to make sure
I just didn't know, like, when do you use, like,
when you use those equations.
when do you use each of the different ones, or what is each
So
one?
when you're gonna, whatever equation you're gonna use, do you get the point of the circle? I guess that's the first thing, that I equals all of these different things and V equals all of these different things. Do you get the point of that?
Yes.
Okay.
Yes.
So how you know what equation to use is whatever the question tells you you're finding, that should tell you what a smaller circle to look at. So for example, I think my next question will answer this. So in this situation, this right here, what is the total power? We're asked to find power. We're given voltage and we're given resistance because we know ohms is resistance. When you go back to this circle, we automatically look right here where this P is, because whatever you're trying to find, you want the equation that is P equals. So we also know, looking at this question, like I said, that we have resistance. Oh, where's my question? That we have resistance and that we have voltage. So that means that we need an equation with a P, a V, and an R, because those are the only three things we know. So whenever you're doing math problems for this course, for electricity, you're always going to be given two known values, and you're always going to be needing to find one. So in this example, we're finding power, but we don't have voltage and we don't have resistance. That tells you what one to use, because P, so now we look at all three of these in the green and we need to know that we have voltage and we have resistance. This one right here has a V and an R. So that's how we know the equation that we need to use to solve this problem is P equals V squared over R. So I guess that's how I think about it and how I think the easiest way to know what equation to use when. And it's whatever value you're trying to find, whether it's I or current, V or voltage, R or resistance, P or power, start there. So start in this inner circle. That's what you're trying to find. Whatever two values you're given, find those in the outer circle, and that's the equation you use. Does that make sense?
Yep. Got it. Thank you.
Perfect. Yeah, of course. I hope that helps. I really think that this helps a lot, having it in like a circle representation. If it helps you to write down all of the equations in a row, do that too. I just think this is an easier way to kind of visualize it when you're doing a lot of math problems. So let's kind of work through this and then stop me at any point if it doesn't make sense. And we'll do a couple more examples, and hopefully by the end of this, it'll be very clear. So This is where I talked about at the beginning. This is where we add another layer from last week. So we already did Ohm's law where we did, the basic equations of I equals P over V. But this is when it adds another layer. So looking at this question, so it says a circuit with 10 volts and 200 ohms of resistance, what is the total power in wattage? So power isn't just a number divided by a number, we have to square it because that's what it tells us to do for this equation. So again, we use P equals V squared over R. So let's write that just so we have it. So we know that we're doing P equals V squared over R. And hopefully everyone knows why we're using that equation. Again, it's because we're finding the power. So that's the thing that we're looking for. And we're given our voltage and we're given our resistance. So all we do is 10 squared, because that's our voltage, divided by 200. So whenever you're squaring a number, when you're typing it in your calculator, I wouldn't type in 10 squared divided by 200, because sometimes depending on what calculator you have, it might mess it up because you have to use parentheses. And so what I would do in your calculator, I would type 10 squared or do 10 times 10, because a squared just means you're multiplying that number by itself. So 10 times 10, we already know that's 100. And then obviously our 200 just divided by 200, and that's how we got 0.5 watts. So just to kind of walk through exactly what we did there. So we had power equals voltage squared divided by resistance. We know our voltage was 10, and we know that 10 squared is 100 because 10 times 10 is 100. And we just did 100 divided by 200 and got 0.5. So I'm going to stop there, make sure everyone understands it. The other thing to note here is that you can see in this problem, we have a decimal. So don't think your answer is wrong. If you ever do get decimals, we'll get decimals a lot in this course. That's kind of why we talk about rounding too in somewhere in your math side of the course, just because you might have to round some of your watts up or some of your voltage, whatever you're trying to find. But does this problem make sense to everyone? Do you understand why we use this equation? Why we had to do 10 times 10? Is that clear? Perfect. Everyone else good? Great. Okay, let's do a couple more. And then if it's clear, you guys are good to go. Ask
I have a
questions.
quick question.
Yeah, of course.
And I know it's just out of my curiosity. So why do we always have two numbers? Like, how do you figure those out if you don't have those two numbers? Is that always going to be a thing? Like you'll always have those?
So that's the thing about math. Whenever you have an equation, if they want you to solve it for a numerical value or like find a numerical number, you only should always have one unknown. For example, when we did this, oh, my annotations, one second. So like, look at here, when I showed you this equation, Req, which is just total resistance equals the sum of all your resistors, you only had one unknown. Your only unknown was that total resistance. You knew every other thing in that equation. That's why you could solve it. It's the same situation for what we're talking about right here in this problem. So because looking at this equation, we have P equals V squared over R. In order to actually find power, you have to know what two values are. Like there's no way to solve P equals V squared over, what was it, R, right? There's no way to solve this, and there's no way to solve for P unless you're given voltage and resistance. So I guess that's why for this class, when just doing like this simple like math for now, whenever you're trying to calculate it, you're always going to be given the values that you need. You're always going to be given two values since we're always finding one, I guess.
Okay, I guess I'm just like, thinking further into it when I'm like maybe doing it or anything like that. Like I was just, because I didn't know.
I totally get it. So like, it's kind of like, let's say this is like totally made up, but let's say we had an equation that was power equals V squared plus, or V squared over R plus, let's say an X or whatever it is, whatever your equation is. Even in something like this, the only way to solve for P, which is what we want, is all of these letters you have to be given the value for. So you're never going to be asked to solve a problem that you don't have enough information for. So it's never going to try to trick you. Whatever the equation you're supposed to use, you should have every single variable that you need except one. And in this case, it was P, right? Because we knew, obviously the X wasn't there. But in this case, the only thing we didn't know was P. And that's how it's always gonna work. You're always gonna have at least two things, especially for this, because it's,
So it's just basically the simple knowledge of getting the equation down and being able to understand it, let alone then knowing where the numbers come from.
exactly, yep, it's the, all you have to know as far as where we are right now, as far as Ohm's law and understanding it completely, it's just knowing this, knowing that whenever you use this circle, you're always gonna be given two values. So that should help. Whenever you have to do a problem where you're using this table, you're always gonna know two values, you're not gonna know one. And the one value you won't know is whatever you're trying to find in that inner circle.
Okay, cool. Yeah, I was just going way too far into it, I guess.
No, I totally get it. That's how I am too. And sometimes I apologize because I love math. So sometimes I probably overcomplicate it. So if ever I overcomplicate it, tell me and I'll break it down in a easier way, or I can explain it differently. So, okay, so this example makes sense to everyone. We're good here with the, this was the problem we just did. I'm gonna move on. Same idea. In this situation, we're gonna follow the same steps we did for the last one. So what is power? Okay, right away, we know that we're doing something that's P equals. So what is the power in watts at a load with 20 amps of current and 20 ohms of resistance? So those are your keywords there. And this is a perfect example again of how we're given two, we don't know one. So now if we look back at our table, we need to find one that has in the P in the inner circle, and then finding one that has current, which again is I, and resistance, which is R. So if we look back at our circle, we look at our P, because that's what we're trying to find. We need one with I and one with R right here, I squared times R. And that's exactly what I did. So we'll write this equation out. And that's I squared times R. And it's the same steps I did for that last problem of how I figured out that equation. I just looked at that circle, looking at this problem statement. I knew I was trying to find power, and I knew I was given current, and I was given resistance. So I found the equation that had all three of those. So this is the equation I needed. So now you just do the math, plug in your calculator. We know our I is 20. We know 20 squared is just 20 times 20, which is, I actually don't know off the top of my head. 20 times 20 is 400. So let's do this in a different color. We have P equals 400, which is our I squared, times our resistance, which is 20, and that is 8,000. That's a horrible zero, but it's written here too. So just to kind of run through that again, how I did that. So we looked at the problem. We knew we were looking for power. We knew we were given current and resistance. We found the equation on the circle that had both of those. Then we do the math. I squared is just our current squared, which is just the number times itself. So 20 times 20, if you plug that in your calculator, you would get 400. And then we multiplied it by the resistance, because that's what our equation told us to do. Our resistance was 20. 400 times 20 is 8,000. And that is your answer, 8,000 watts, because that's the unit for power. Same situation, just different knowns we were given. So it's a different equation. Is this example, does that make sense how we did that? Why we did that?
Yeah, I think so.
Perfect. Okay. Great. Let's move on. So this one is basically the same thing we talked about at the beginning, but you'll see that the next question blends both of these concepts together, which is why I'm doing an example on this. So like we talked about here way at the beginning, when calculating total resistance, it's the sum of all your resistors for a series circuit. So let's say we had a series circuit with 5 100 ohm resistors. What is the total resistance? So all it is just R1 plus R2 plus R3 plus R4 plus R5, because that's exactly what this equation tells us right here. So that's how, for this problem, we got 500. So we just added all of those resistors together. And you could also do 5 times 100. It's the same thing. That's all I was showing here. If you want, I think it'd be beneficial to draw this. So let's do that just so you know, like visually what this is looking like. So obviously a circuit's a square. When we're talking about, can I highlight it? No, I need to annotate. When we're talking about resistors, kind of how they showed, they just draw them like these like weird squiggly things. So this, we have 5 resistors. So we're gonna have 5 of these somewhere along our line. One there too. So that's what that would look like. And then obviously all of these would say 100. I'm not going to write all these because it's going to take too long, but 100 ohms. And this is like the sign for ohms, this weird horseshoe thing, if you ever see that in a problem. So that is what it would look like. And that's kind of like what this looks like. This example, how it has R1, R2, and you see that little squiggly there. That's what I was trying to draw here. But we have 5 because it says we have 5 resistors, all that are 100 ohms. So we just added R1, R2, R3, R4, R5 together. I'm gonna move on. If you want me to stop, just holler at me and I will stop and re-explain anything. Okay, so this is where this can get confusing and you see a lot of numbers and it's stressful, and it's really not that hard. You just have to break it down component by component. So we're gonna follow the same steps we did in the last couple of problems, and it was, what are we trying to find? So we're trying to find, right here it says, what will be the total current in the circuit? So we're trying to find current, and we know that we're given volts and we were given resistors. So we're given R and we're given V, and we're trying to find current. So we look at the table or the circle. I'm not going to go back to the circle, but it's this equation, I equals V over R. If you look at your circle, if you have it, you'll see that's what it is. But this is where you get a lot of numbers and you don't know how to plug them in, and this is where people get confused. So in this situation, they're giving us the resistors, but they're not giving us the total resistance. And we know that because it doesn't say the resistance is, it just says there are 3 resistors. And what we talked about just a minute ago was that in order to calculate that total resistance, you need to add all of your resistors together. So this problem has a second step, and that is right here. We have to find that resistance. So the way that they would do this is just sum them all together, R1, R2, and R3. So they did 12 plus 5 plus 3, which is 20, because those are our 3 resistors that we have. And then you can solve the math, and you do it just like you did the last problem and just like you did all of them last week. And it was just I equals V over R, which is just I equals voltage, which was 10 right here, divided by our resistance, which was 20, because we know that because 12 plus 5 plus 3 is 20 here. So it's 10 divided by 20. So the way that you're going to kind of know if you have to add all these numbers together is it's going to say it just like this, like you have this many resistors. It's not going to tell you the resistance. So it's just basically it's implied that you have to calculate the total resistance. So that's kind of how this kind of gets a little bit complicated. And this is where we have an additional step. But I'm hoping that, does everyone kind of understand like why we had to do that extra step of adding them all together?
Yeah, it makes a lot of sense to me now that you're saying it.
Okay, great. So like kind of this is also something that like last week when we were doing a problem like this where it was just I equals V over R, it's because they didn't tell you. But if you go back to last week's quiz, all of the problems say you have a circuit with 10 volts and a resistance of 20. They don't tell you, you know what I mean? They like skip this step right here. So we're like, this is like kind of where it takes it, you know, just it gets a little bit more complicated and where you learn more knowledge about how you actually calculate a value like resistance. But
I think that was a lot of complication at first, you know, like just understanding what we were getting to. Like we didn't get to it yet, you know, because we were in the first week, but it was just like, yeah.
Yeah, definitely. No, I totally agree. And that's why it's hard, because it's like, I like to give you like a heads up, like how I'm giving you, like how I kind of try to give you a heads up here. This is what we're going to talk about next week, but I don't want to give you too much ahead because then I think it's overwhelming. And I think it's That's why it's important to learn the fundamentals first, like learning this and learning like the equations and how to use them is really, really important for when we get to steps like this and we have to, almost take it backwards and like calculate another value. So it definitely, it can get challenging. And that's why this course, it's really not that bad, but like, it's just learning the fundamentals first. And then, making sure when you have questions on the easier stuff in these weeks, you ask them so that in the weeks to come, there's nothing.
It's important. It's important to keep going though, because I was like getting really frustrated at first, and but it's just important to keep going.
Definitely, yes, I totally agree. So just let me know too. Like I do this hour, but I would be more than happy to, Zoom any of you one-on-one. If there's anything you're confusing, I will find a time that works for you. Send me an email. I can try to explain things on email too. I know online classes can be hard. So whatever I can do to like explain things better, explain things so you're not frustrated, I will do everything I can too. So, all right. So the last little bit here, this was the main complicated thing for this week, just learning how to calculate power by using these squared equations. And then this idea of having that additional step of calculating your total resistance and then the mashing of the two of calculating your total resistance to calculate something else, which is what we did here in finding current. So last little bit's pretty simple. It's the concept of voltage drop. So basically all you need to know is that a voltage drop at each specific resistor is the resistance at that resistor. And I will explain it in this problem, and then it won't be that confusing. The next slide, I'll actually explain what a voltage drop is. But so basically, this is what I mean. So let's say you have a problem like this, where you have a series circuit with 300 volts and 3 resistors of 12, 5, and 13 ohms. It says, what will be the total of all voltage drops added together in this circuit? So right here, it says that the voltage drop at each specific resistor is the resistance at that resistor. Let's start there. So what that's saying is the voltage drop at each specific resistor. So we know here our resistor is 12. So that means our voltage drop is 12. So basically whatever your resistor is at a given point in time, that's what your voltage drop equals. So at the voltage drop on the 12 ohm resistor is just 12 volts. The voltage drop on the 5 ohm resistor is just 5 volts. And the voltage drop on 13 ohm resistor is just 13 volts. So I know that like doesn't make sense, but I would just that's something I would just memorize when you see voltage drop and you have to calculate it at a resistor. Just know that there's no math. All you have to do is whatever the ohm is, that's what the voltage is. And this is just only referring to voltage drop, not voltage. So these should be easy questions for you. If you ever get one, it's, what's the voltage drop on the 5 ohm resistor? It's just 5 volts. What's the voltage drop on a 100 ohm resistor? It's just 100 volts. But that's really all this is saying. And then it says the total of all the voltage drop is just the sum of the resistors. So 12 plus 5 plus 13, which is 30, if I did my math right. 2, 3, up 30. So that's all it's saying.
So it's just kind of the same.
Yeah, it's just the same. That's all it is. It's just this is worded really like weird because this is what it shows you if you typed into Google what's a voltage drop. It just says the voltage drop is this at this, but just know that the drop is whatever the resistor is, and the total voltage drop is the sum of all your resistors or your total resistance. That was a lot of saying resistor. Is that okay? Like this is just like a math thing, but you don't need to know why this is. Yeah, just know that that's the case. So voltage drop at every resistor is whatever that resistor, whatever ohm that resistor is, but in volts. So that's a little bit basically what a voltage drop is. So basically, it has to do with like electrical potential, which is a term when dealing with like energy, and it's really kind of a complicated term. But I have it written here just in case you want to know, but like really it's just it's not that important for like this applications or even anything really. It's just the main idea is like if you can do this, but and then so this is only other thing worth noting. So Kirchhoff's law, which we talked about, which we'll talk about later on, but it's basically what that is saying is the sum of the voltage drops will equal the initial voltage. So if we look back at this problem, I'm going to point out one thing that you probably didn't notice, and that is our total voltage was 30, and that's what happened when we calculated our total resistance. And that's not always going to happen, but it's always going to happen when we're talking about voltage drops. So the sum of all your voltage drops is always going to equal the initial voltage. And that goes back to the definition that's complicated, and it has to deal with, basically your voltage drop is in your circuit. At some points, your voltage isn't going to be the same throughout. And that has to do with your resistors, because your resistors are, impacting your voltage. And that's the whole point of adding a resistors. But whatever your initial voltage is, your voltage drops that happen have to equal. So that's there's a lot of different terms when talking about voltage drop that are related. So I think the best way to kind of show this again is to show the things that are related. So if we look back at Kirchhoff's law, it's telling us that the voltage drops equals the initial voltage. So that's why right here, we had 30 volts, which is our initial voltage. And that's why our voltage drop, which is just the sum of all your resistors, was 30. This was our voltage drop. I'm going to write VG so you remember. So that's the first step that are always the same. So your initial voltage and your voltage drop are always the same. The second thing that's always the same is whatever your resistance is at a particular resistor, that's what the voltage drop is at that particular point in time. So the voltage drop on a 12 ohm resistor is 12 volts. So those are just kind of how all of the pieces tie together. If you want me to send you this so you can kind of remember it, I think that's probably the best way that I would remember it. If you're struggling with the quiz, maybe write down an example like this where it shows okay, these are the resistors, these are how they relate to the voltage drop. Here's how my voltage drop relates to my initial voltage. I know that was kind of a mouthful, so but that's the last thing I have. So is there anything that you want me to go back on? Is there anything that's confusing? Was this confusing? Because it was a lot of saying resistance 10 times. So I'll take it over to you guys if anyone has any questions. If you don't have any questions about anything I talked about for week 2, I think this is a lot of information that really should help you with the GenNet quiz. I don't touch too much on the Amatrol, but if you need help with that, I'd be more than happy to meet you. Just email me. We can figure out a time to Zoom. But that is all I have. So any questions?
Okay, so I know this is going to sound a little weird, but how much does the reading pertain to what we're doing?
The reading for Amatrol?
Like the chapters. It says chapter 1, we had to do on week 1, and then chapter 2 and 3 on the second week in the book.
Oh, there's the textbook they give you.
Yeah. So how much does that pertain to that? Because I'm just struggling reading it, honestly.
Okay, this is my suggestion for you. And it's that the textbook is supplementary. All this course is already created for you. And so it just is kind of preloaded in there. And I think that the textbook, if you understand what I talked about here, if you watched all of the YouTube videos in that week, that should be sufficient enough to succeed in this course. I wouldn't say, especially if it's confusing you. I think that a lot of the information they probably talk about in the textbook is stuff that you might learn later on. So maybe it's good to just look at or maybe just skim over, but your primary focus, I think, should be the YouTube links that they have in every week. That's the best information for what's going to be on the GenNet quiz. And also what I try to summarize in this hour should be the best information you have to succeed in that JetNet course. As far as the Amatrol goes, it is kind of just like reading the Amatrol. Like, I know they kind of do a little bit like there's like reading pieces and like little like activities, simulations in Amatrol. That's the best way to like do well in the Amatrol quizzes. But I think that having you sit there and like read the textbook and try to understand everything, like it's probably overwhelming, and I don't think you need to.
Yeah, that's where I was definitely struggling on. So that definitely helps you saying that, because I understand, the videos and stuff, like I can get through that, but actually reading that and just like, I kind of take too much in and I'm just not,
Oh,
grasping.
definitely. Yeah, I'm even looking at it now, and like I think it's confusing, the textbook. I think it's way too. It's a lot of information. I think honestly they give you this more because like everyone learns different ways, and some people do learn by sitting and reading a textbook. So I think that's kind of why they have it here. Just
Right. Yeah, of course.
but yeah, I think you're fine. Doing what you're doing should hopefully be enough, and I think it will. And then in the weeks that are harder.
Yeah, that helps so much. Thank you.
Oh, of course. Anyone else? Any questions at all? Trying to think if there's anything else worth saying. I guess all in all, just like make sure you keep doing what you're all doing. Do the quizzes, do the Amatrol stuff, and you should be all right for this course. Even in the harder weeks, it doesn't get too bad. It really doesn't. So yeah. So any questions? If not, you're free to go enjoy your rest of your night, and I will see you next Thursday. Thank you all for coming.
Thank you.
Oh, of course. Have a nice night.
You too.
Have a good night. Thanks. Hi, Ignacio. Do you have any questions? I see you're still on. You're muted if you're trying to talk. I hear little red mutes on. There's a thing, and there's the mute in the corner. If you click that, it'll let you speak. No.